All right, here we go. So lesson number 6 is on 14 basic functions and transformations. So I'm going to talk about a bunch of parent functions. Okay, so parent functions are the functions with the most basic shape. So like a parent function for a parabola is like it's in a weird color. I don't know why it's that color. All right, so we're going to talk about 14 functions that you guys definitely need to know cold. Most of you already know. You just don't know that you already know them. All right, so constant function is f of x equals c. So if you have, for example, f of x equals 2, like the one shown above, its domain is going to be all real numbers, so negative infinity to infinity. And the range, there is only one y value. Okay, that y value is whatever c is. So we just say c. Sometimes people will draw it with little brackets around it, meaning the set of all the numbers that are in that bracket, but it's just c. All right, so the identity function, f of x equals x. Again, its domain is negative infinity to infinity. Its range is the same thing, negative infinity to infinity. Right, this is the line y equals 1x plus 0. Its slope is 1. Its b value is 0. See how it goes through 0 and it goes up 1, right 1? So it has every point, like 5, 5, 6, 6. It has all of those points. All right, the absolute value function. So if you did a little t-table for the absolute value function, you would see that every time you have a positive number, you get the same thing out. But every time you have a negative number, you end up getting the opposite out.
Wouldn't the m be 1?
Oh, I wrote 0. Whoops, I should have said m equals 1. I think I said m equals 1, didn't I? I think I said it, but I wrote the wrong thing. I was already moving on to b. All right, and then negative 2 and 2. So, Evan, can you just write your name on the board there? All right, so that means we have 3, 3 and 4, 4, 5, 5. But if we have a negative number, it ends up being the positive version of the number, right? So the domain is going to be all real numbers. We can plug in anything for x. But for the range, what is the smallest y value we get out? 0, exactly. So it's 0 to infinity. All right, the greatest integer function. Do you guys remember this one? I see some of you guys rolling your eyes. The greatest integer function, we also call it the step function. You might see it as intx or f of x equals, it's like a fancy like bracket thing. It's like a bracket with an extra stem. So you could see that. And basically what it means is for everything you're basically rounding down. So if you have the greatest integer function of 3.5, it's the greatest integer that's less than or equal to that. So you're going to round down to 3. 3.9 rounds down to 3. 3.99 rounds down to 3. But once I get to 4, I go up to 4, right? 4.1, 4. 4.2, 4. Does that make sense? So it's just flat lines. So it's going to look like that. So its domain, it does have everything. It's negative infinity to infinity. You can plug anything into it. But the range, what would I write for the range? Close, not whole numbers. Whole starts at 0. All integers. So the range is all integers. Does anybody remember the fancy way that we can write all integers? Yeah, Julia? Close. That's rational numbers. Q is rational. It's a Z. I know. It's a Z with an extra stem. All right. So those are the first 4 that you need to know. Think you can do that? This one's an easy one. Quadratic function. This is f of x equals x squared. Its domain, negative infinity to infinity. Its range, 0 to infinity. So when I'm putting a bracket, remember that means it includes that point. It includes 0. Cubic function, another easy one, negative infinity to infinity, and it's also negative infinity to infinity for its range. Reciprocal function. This is one you've kind of seen before, but we haven't really called it the reciprocal function. So f of x equals 1 over x. So if you think about how this works, if you did a t-table, if you plug in 1, 1 over 1 is 1. If I plug in 2, though, I get a small number. I get 1/2. If I plug in 4, I get even smaller, 1/4. So if I want to get a really big output, like if I want to get 10 out for the y value, what do I plug in for x? If I want 10 out, 1/10, right? So it's like the closer you get to the axis, the more it shoots up. So if I'm at 1/10, that's when I'm getting 10 and going way up there. And the further away I get from the y-axis, so as I'm moving to the right, the closer it gets to the x-axis, right? So that's what the reciprocal function looks like. And it's the same for positives and negatives. So if I plug in negative 1/2, I get negative 2. So negative 1/2 gives me negative 2, and so on. All right, so its domain is almost all real numbers, but notice we're skipping over one number, 0. So it's negative infinity to 0, union 0 to infinity. So that means that we skip over 0. All right, and its range actually is exactly the same thing. So it's negative infinity to 0, union 0 to infinity. So we're also skipping 0 here. So that's because we have a vertical asymptote and a horizontal asymptote of 0. Y equals 0, x equals 0. All right, the square root function, we can't plug in negatives into the square root, so we don't have any negatives that we're going to put in. So its domain ends up being bracket 0 to infinity. And because of that, then its range is also bracket 0 to infinity. We can't get a negative out either. So all of these should be somewhat familiar. Exponential function, e to the x. The most important point right here is that it goes through 0, 1, right? If you plug in 0, you get 1, right? E to the 0 is equal to 1. And it shoots up pretty quickly. Its domain is negative infinity to infinity. So you can plug in negative numbers. Like if you have e to the negative 2, remember that's just 1 over e squared. That's a number. It's just very, very tiny. All right, and then the range, we actually cannot get 0 out. We can't do e to some number and get 0 out. Does that make sense? Yeah, so it doesn't work. So we can't get 0 out. So for our range, we start at 0 and we go to infinity. And then the natural log function ends up being the inverse of e to the x. So instead of going through the point 0, 1, which this last one did, this one goes through 1, 0. And the domain and range are just switched. So its domain is going to start at 0 and go to infinity, and the range is going to be negative infinity to infinity. Okay, so you can't take the log of a negative number. You can't take the log of 0 either. All right, and then things that we will talk about extensively this year are sine and cosine. Okay, you do not have to memorize everything about this graph at this point right now. Just know that its domain is everything. And its range, even if you think about the unit circle that we discussed at the end of the year in Algebra 2, this point up here was 0, 1. This point on the right was 1, 0. This point down here was 0, negative 1, and negative 1, 0. And I talked about the x value was the cosine of theta, and the y value was sine of theta. So the biggest number I ended up getting out for sine was 1. So the sine curve, the highest it goes to is 1. I can't even read these. These are blurry, but this should be a 1 here. So 1. And the lowest it goes to is negative 1. So its range is bracket negative 1 to 1. And it ends up being the same for cosine. The highest it goes to is 1. The lowest it goes to is negative 1. So its domain is negative infinity to infinity, and its range is bracket negative 1 to 1. So we'll talk about that a lot. That is what precalculus is all about, trigonometric functions. Okay, and then the last two that I want you guys to know are the cube root function and the logistic function. So the cube root function looks kind of like y equals x cubed. It's just on its side. Okay, it's the inverse. So its domain is going to be negative infinity to infinity, and its range is negative infinity to infinity as well. So like, you know how the x cubed function, we had the point 2, 8. Well, the cube root function, since it's the inverse, it has 8, 2. Right? It has the opposite points. And the logistic function, this is basically a model for any kind of population growth. So it's kind of morbid, but basically a population can grow and grow and grow up until a certain point, and then people die off. So it's very morbid, or anything. So basically, there's some kind of horizontal asymptote. So for this parent function, its horizontal asymptote is at 1. And there's also a horizontal asymptote down here. You can actually have more than one horizontal asymptotes. So it's at y equals 1 and y equals 0. So its range is all of the numbers between 0 and, well, actually not including 0. So 0 to 1. I guess you should technically include 0 in a logistic function. You could have 0 for your population, right? But we're not going to include it. All right, and then the domain should be negative infinity to infinity. So this parent function does not have a 0 included. All right, so most of those you guys already know. Some of them are new to you, so kind of look those over, know their basic shapes. You don't have to know every single thing about the logistic function right now, like that it goes through 0, 1/2. You don't need to know that, but know that it has 2 horizontal asymptotes at least. Okay? Okay, so let's talk about some transformations with these functions. So ideally, when you get out of precalculus, you should be able to look at any graph and say, oh, I think I know what that graph's going to do. It's going to be like a cube root, the cube root shape, and it's going to be shifted over right 3 and up 2, and you can basically sketch it very quickly without using a calculator. Okay, so that's the goal. There was a boy a few years ago who could do it for any function. We would just throw him random functions that we didn't even really know what they looked like, and he was very good at it. He always knew what they looked like. So you could be him. All right, so there are different rules. If you remember, vertical shifting is when you have your function and you just tack on a plus c or a minus c or a plus k or minus k, whatever. Horizontal shifting is when you have inside of your function, like inside of parentheses, instead of just x, you have like x plus 2 or x minus 2, and it does the opposite of what you think. Vertical stretching and shrinking is when you have the number outside of your function. And horizontal stretching or shrinking is when the number is inside the function, and again, it does the opposite of what you think. Okay, so our rule is anytime something's inside with the x, it does the opposite of what you think. Anytime something's on the outside, it's affecting the y value, and it does exactly what you think. Okay, so if you see something like f of x equals 1/2 x squared minus 3, you should first be able to identify the parent. So its parent function is y equals x squared, which is a parabola. And then you should be able to list the different transformations that are happening to it. Now, the order of these does actually matter. Okay, so I'm going to be more of a stickler for this in pre-calc than I was in Algebra 2. Okay, so think about as we're plugging a number in for x, we would square it. And then what would be the next thing we would do if we were plugging a number in? We would multiply by 1/2. That has to be the next step. So if I see 1/2 of x squared, notice that it's not 1/2 in parentheses of x squared. Something buzzing around behind me. I'm a little scared. All right. It is not 1/2 of x squared, right? Or it's not 1/2 in parentheses. It's 1/2 is on the outside. So because of that, it's affecting the y value. So if I take all of my y values and I half them, right, it's going to do a vertical compression. So this is a vertical compression. By 1/2. So it's just going to flatten it down a little bit. And then we're going to go down 3. So when we have a minus on the end, again, it's affecting the y value. It does exactly what you think. So if you take the y values and you subtract 3 from them, it moves your graph down 3. Okay, so it says sketch the original graph and transform the same graph on the same grid. So you guys might want to use some color pencils or something for this. I can get some color pencils out if you want, or just different colors of pens or whatever. I'll get some color pencils. All right, so you guys can use different colors for the different steps along the way if you guys want to. So let's say I use a black marker for the first one. So I have y equals x squared. So I know that that goes through 0, 0, and 1, 1, and negative 1, 1, and then 2, 4, right? You don't have to do every single point, and then 3, 9, 5, 6, 7, 8, 9, and negative 3, 9. So here's my basic parent function. So that's step 1. All right, so the next thing that I'm going to do is I'm going to vertically compress it by 1/2. So what that means is that every y value that I had, I'm now going to take half of it. So when I had 0, 0, it still stays at 0, 0, because if I do half of 0, it's 0. When I had 1, 1, it's going to go down to 1, 1/2. And maybe the best one to see is 2, 4 is going to go down to 2, 2. Yeah. It will be. And then the next one is 3, 9, and that's going to go down to 3, 4.5. Okay, so that's where we're at now. So we just kind of smushed it down a little bit. And the thing that people don't like about that is they think, oh, wait, but it's wider, it's bigger. Right, but we smushed it like taffy. It gets fatter as you push it down. All right, and then down 3, that's the last one. Sorry, mine's red. You guys can't see my red, can you? It looks like black on your screen. Okay, so let's do green. So if I do down 3, then that point 0, 0 is now going to be at 0, -3. And the point that I had that was 2, 2 is going to be at 2, -1. And -2, -1. So we've now shifted it down. That is our final answer. Does that make sense? So the green one is what add. So you just do one step at a time. All right, so the next one. So we have 1/2 x - 3 cubed plus 1. So this parent is y equals x cubed, which is I always call it the snake function. It's like that. So it goes through 0, 0. It goes through 1, 1, -1. I'm off a little bit. Hard to figure out. -1, -1, and then 2, 8. So it shoots up pretty quickly. Two, 4, 6, 8. I get something like that. My little machine's not calibrated correctly, so I'm like off. It's hard to grab. All right, so the next one. So after we draw the parent function, what is my next transformation? What direction do I move? When I have x - 3 in parentheses. When I have x - 3 in parentheses, I go right 3. Exactly. Anytime something's inside parentheses with the x, it ends up doing kind of the opposite of what you would think it does. So when you see x values -3, it's actually x values added to 3. So we're going to do right 3. All right, so I'm going to, instead of having 0, 0, I'm going to have 1, 2, 3, 0, and so on. All right, and then I have 1/2. So that's going to be a vertical compression again by 1/2. So really the ones that are super high, those are the ones you can really see. So instead of having this point that was at 8, so is that what, 5, 8, 5? Is it 5? Yeah, 5, 8. It's now going to be at 5, 4. And then 0, 1 still at the same height, and then I'm going to have 1, -4. So it's just smashing it in a little bit. Still kind of looks the same. They're very close. All right, and then the last thing is up 1. So up 1, so just move all of those last points that you had up 1. Okay, so ideally you won't have to do this every single time. You won't have to do every single transformation. You're just going to know where the graph is going to go, and you can just draw the final one all at once. Do you guys understand what I'm saying? So, all right. So it says note, and we talked about this a little bit last year. If something has 2 horizontal transformations, you must first factor in the inside of the parentheses. For example, if you have f of x equals 1/2 x - 6, it looks like the 2 transformations are that you're moving things right 6, and then you're doing a vertical, it ends up being a vertical stretch by 2, but you're actually not. So you would think that you were at the point 1, 2, 3, 4, 5, 6. You would think you're over here. But you actually don't do that. And I want to show you on your calculator why we don't do that. So go ahead and get your calculator out, and we'll put this in. Oh, I'm still in parametric from the other day. All right, function. Okay, so clear. All right, so I'm going to put in parentheses. I'm going to do 1/2, so I'm just going to do 0.5 because I'm lazy. X minus, what did I have, 6? Yeah, squared. I'm just going to do zoom 6, so my standard window. Okay, and I get it over there. So let me move it over a little bit. So my window, I'm going to go up to an X max of 20. Okay? So it's not at 6. Can you guys count? Where is it at? Where's the vertex at? It's not at 6. It's at what? 19? I heard a mumble. It's at 12. Do you see it's at 12? You're graphing along with me. It's at 12. So it's not what you would think it would be. Like when you look at that, it looks like it's been shifted right 6. It did not shift right 6. It shifted right 12. Okay? So there's some weird things that go on. So it says, however, if you do this on your calculator, you'll see that it actually moved right 12. You must factor the inside. So you're going to pull out whatever number you have here. So you're going to have 1/2, and then you're going to do x minus, well, what would you need? You would need a 12 in order to get that 6. So you're dividing by that number. If you divide by 1/2, it's multiplied by 2. Okay, and then since I don't really like to have a 1/2 x minus 12 and then all of it squared, what I tend to do is I square the 1/2 and I get 1/4, and then I do x minus 12 squared. I write it in vertex form. So I get 1/4 x minus 12 squared. So it says this is why vertical compression looks like a horizontal stretch. It ends up just being by different numbers. So if I called that a horizontal stretch, I would say a horizontal stretch by 2 because of the 1/2, right? Horizontal stretch by 2. Or a vertical compression by 4. Okay, so they mean the same thing, it's just different numbers. All right, so number 1, so it says describe how the graph of g of x equals 2x minus 4 quantity squared plus 6 has been transformed from its parent function. All right, so what I have to do is I have to pull out the 2 from both of them, from the 2 and the 4. So I need to rewrite it as 2 times the quantity of x minus 2 squared. Yeah. So I continue one more step, and I bring the square into both the 2 and the x minus 2. So I write it as 4 times x minus 2 squared plus 6. So I just go ahead and I square that number, the 2. So how has it been transformed from y equals x squared? It moved right 2. There was a vertical stretch by 4, and it moved up 6. Those are the 3 transformations. Do you understand that? All right, so number 2, so it says, what is the new function after f of x equals the square root of x has been horizontally stretched by a factor of 2. So if I see horizontally stretched by a factor of 2, what do I need inside the square root? Not 2. I need 1/2. Right? It's the opposite. Instead of multiplying by 2, I end up dividing by 2. 1/2 of x. Then it's going to be shifted right 6. So I want to put in parentheses x minus 6. And then all of it's down 3. So it's going to look like that. So I'll call this g of x for the new function. So I would write it as the square root of 1/2 x minus 3, and then minus 3 on the end. Okay, is this all coming back to you? Are you remembering the transformations? All right. All right, so then we have reflection. So something reflected across the x-axis. Like, it's not a big deal if we have a quadratic function and we reflect across the x-axis. It just moves it down here, right? That's all it does, okay? Some of the other ones are a little bit harder. But if I have x squared, it just flips it over. All right, what we end up doing is we put the negative on the outside of the function. So we have negative f of x. If we reflect across the y-axis for a parabola, though, it does nothing, right? The points that you had before are just now on the other side of the axis, becoming other points that we already had before. So across the y-axis doesn't do much. But it does when we talk about things like the square root of x. So it says the graph of g of x equals the square root of x is shown below in dotted lines. Sketch the graph of p of x equals negative x under a square root. So if you have negative x under the square root, that means all of your x values become negative. All x's become negative. Just like this last one, since the negative was on the outside, all y's become negative. That's why I went downwards. So it ends up being the same graph, just on the other side of the axis. Okay? And sometimes in pre-calc, you won't even have a function. It will just say your original function was f of x. Describe what happened, or write the new function. So that's what this example says. So it says, describe how the graph of each function can be obtained from the graph of f. So if we have f of x plus 4, what happened to my graph of f? Where did it move? Left 4, exactly. All right, if I have f of x plus 4, up 4, exactly. Negative f of 2x, what did the 2 do? Horizontal what? It's opposite of what you think. So when you see 2 times x is actually dividing by 2. So it's a compression, or shrink, I heard somebody say, by 1/2. And then the negative out front, does it change the x values or the y values? If it's out front, the y values. So if your y values become negative, if you have some kind of graph, and you had a point that was up here, and its y value became the opposite y value, it reflects across the x-axis. So reflection over x-axis. Oh, I should have mixed it up. So f of 2x, again, horizontal compression by 1/2, and then this one goes down 1. Okay, it says if we have f of x equals the absolute value of x, how can we transform the graph so that the point, the vertex, of the absolute value is now at -5, 3? So if we want our original, which started at 0, 0, and we want the new to be at -5, 3, yeah, how do we have to move it? What do we do? If not, -2. So what do we do to the x values? Yeah, we go left 5. So in the absolute value, we're going to have x plus 5 to go left, right? And then we want to go up 3. So we just tack on a plus 3 on the very end. That's it. X plus 5. And absolute value is plus 3. All right, so number 3. So sketch the graph of g of x equals the quantity of x plus 1 squared minus 3, not by plotting points, but by starting with f of x equals x squared and applying transformation. So can you do this without the various steps? So we know what the x squared looks like. So if I have x plus 1 minus 3, that means I move left 1, down 3. So my new vertex, instead of being at 0, 0, it's going to be where? -1, 3. That's why we called this before. We called it vertex form. We talked about that earlier this year. Oh, dang. I said down 3, didn't I? Darn. Yes, it is negative. I believe Alex Pegram got that. You may put your name on the board, Alex. All right, so let's see. So -1, -3. So I'm going to do -1, 1, 2, 3. So I have -3. It's right there. And that's just going to go up from there. Now, none of the other points have, these haven't stretched things, right? We haven't stretched or compressed we haven't compressed at all. So think about where we started with y equals x squared. When we had y equals x squared, we had 0, 0, and then I always did 1, 1, and -1, 1. So you're going to go up just 1. So left 1, up 1, right 1, up 1, right, to get the other 2 points. And then you could go up 2, 4 as well to find the other one. So it looks like that. All right, so this one says sketch the graph not by plotting points, but starting with f of x equals the absolute value of x and applying transformations. So do you guys notice that this is one of the weird ones? You have 2 horizontal transformations. So it's like red flag, lots of weird things. All right, so we're going to rewrite it. So I'm going to do 1/2, and then I'm going to pull out the x minus, instead of -3, I'm going to put 6. Because when I pull out that 1/2, if I put it back in, right, it's -3. And you can actually pull the -1/2 outside of an absolute value. So you can do that. As long as it's a positive number, you can pull it out. All right, so we have 3 transformations. So we go right 6. We have a vertical compression. Oh, we actually have 4. By 1/2. We have a reflection where? Over which axis? The x-axis, yep. Then we go up 4. Okay, so be thinking about it, Kyle. You thinking? So previously I started at 0, 0, and I'm going to do all these transformations. All right, so this one might take a couple steps. Okay, so I'm going to go right 6. 1, 2, 3, 4, 5, 6. So I'm right here. All right, and then I'm going to do a vertical compression by 1/2. So really, like, it's kind of like 2 lines with a slope of 1 and a slope of -1. Now the slopes are going to be like 1/2 and -1/2. So we're just going to make it like flatter. So it's going to be like right here. See how I just flattened it out a little bit? Reflection over the x-axis. So that's going to put it here, and then up 4. So 1, can't really tell where my 6 is, man. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4. So that's what your final thing should look like. So it's like, it's up here, and it's kind of flat. Do you guys have that? Tricky, tricky. That's like putting everything together. All right, so how are we feeling about transformations? Are you kind of remembering it? How many of you guys are freaking out? Is anybody freaking out? No? You're not openly going to admit it? Those of you that are new to university, did you do this last year? Maybe. You're not new to university. All right.
Oh, you're right.